So the next talk is very timely given the recent Nobel Prize announcement. We did not know that when we selected this talk for an oral. Kashyap will talk about encoded modern Hopfield networks. And yeah, he will talk more about the Nobel Prize, I believe.
Hi, everyone. Thanks for the opportunity to give this talk about encoded modern Hopfield. Yes, that Hopfield. So the most obvious place to start is here. As everyone knows, this recently, as early as this week, that this was the Nobel Prize in Physics. And this slide is very much last minute because I took it straight off from the Nobel Prize award announcement. But this is a good representation of why I want to give a little bit of a background on why we started exploring this. So the whole idea, if you see the title of my talk, was on trying to get inspiration for making large-scale storage content-aware and make content addressable. And so we started down this exploration to see what is available. And then one of the best ways is to human declarative memory was one of the places to see if we can get inspiration from, and that's where we landed on this Hopfield idea, wherein essentially what they are talking about is okay, you can see my mouse, that's good. Is that these are, the whole idea of this is that these are associative memories which store information in mimicking a part of the brain called the hippocampus. That's what that's what Hopfield networks kind of do, or any associative memory does. And so you can think of it as an energy landscape, and all of the useful information or the memories are stored in what is known as basins, or like the troughs in this kind of valley. And so when you start with a given pattern, like an incomplete pattern, and that's kind of like dropping the ball, which is what this representation shows. And then the way the Hopfield network, it's a form of recurrent neural network. So it over multiple iterations, it kind of comes to this comes to the trough, or reaches the place where it's surrounded by the basins, and if it's done correctly and it has the lowest energy, it finds the actual pattern that's saved. So that's kind of the idea of what the Hopfield network does. So that's where I wanted to start, and then more formally, in a general class of these associative memories, just reiterating here, these are systems that store and retrieve patterns of information. So another way to look at it is that if you have these bunch of these images that's stored in your memory bank, and then you give this partial query of, say, one of those images. So the way the associative memories work is that they have the similarity metric, and then they go through this separation, and then it retrieves from memory the closest whatever was stored, if it is stored. And so the Hopfield network is one such energy-based model, and like I mentioned, these are recurrent. And so in general, you can think of them as a similarity to between what is stored in the memory and what is queried. And then you have a separation form. So the modern Hopfield networks have the softmax. And then you have a projection if you have like two different modalities that you want to query across. So that's the idea. And like I mentioned from that ball example in the previous slide, the lowest energy equates to the optimal solution. So in our use case, we wanted to see if these associative memories can be used to improve current storage systems by improving the retrieval of information, compression, and also to help draw information from across modalities. So that was the idea. But there are some drawbacks of these current Hopfield networks, and I'm going to go through some of those. So the first one is metastable states. So what do I mean by that? So if your energy landscape that you saw is dependent on the closeness of the data in memory. So if you have too many of them which look similar to each other, it leads to something called an intermediate or an state of energy, wherein it doesn't go all the way to that basin in that ball idea, and that's called the metastable state. And so what happens is that if you give some of this partial information like this, you end up getting these metastable states, and just one of them is recovered. Basically, overall, you get a very poor recovery. Yes, and the other issue is that you have to give some sort of a partial information on the same domain to get more information. And you can do hyperparameter tuning, and then there is some improved similarity functions, or you can try improved representation all to help mitigate this. So in our work, what we wanted to see is the first thing we wanted to address is the metastable state problem. We'll come to the give information to get information afterwards. And so this is what we tried attempting. Instead of storing the entire image as is in memory, one of the ideas we wanted to try was explore an encoded representation of it. So for this example, we tried to take an pre-trained or a well-trained image encoder-decoder model, and then you encode and then the encodings are stored in the memory bank. And then when you have this partial query, you also encode it with the same encoder. And then you run the recurrent updates on the modern Hopfield, and then you use the decoder to get back your image. And so what we found was that it does a much better job at improving, recovering a lot more images. And then also, it's a very flexible system, as we'll show, that there's a whole bunch of these well-trained encoder-decoders for which this kind of worked. And the example here I'm showing is from the previous slide, wherein if you just gave the image as is, it didn't do a good job. And so we wanted to explore more as to like, what is it that is driving this? And so in this slide, so what we tried to look at was that if you give, say, in this example, like if you have n number of images stored in the memory bank, and then you've got n of these same half or the retrieval queues. So what you so we ran a cosine similarity between like the queries and all of that stored in the memory bank. And then the diagonals were like the self similarity, and then the off diagonals were similarity with the other memory items or the rows. And so what we saw, interestingly, was that for the different well-trained encoder-decoders, we see that the separation between them was pretty good. So for example, the red is the self-similarity in all of these. And for example, if you look at the images, you see that there's a very high overlap. That kind of explains the metastable. And then as we looked at the different diffusion models and then the discrete VAEs, we saw that the better the separability, the better was the recovery. And so that was, so that was interesting, and then we wanted to further explore as to how much can we push it. And so one of the things that the next thing we wanted to look at was that what else can you see to reduce the spurious attractors or the metastable states? And so just to recall, the whole idea is that you have a similarity, and then you've got a separation, and then you have the projection. So for the similarity, we tried like a dot product between the query and what's in the memory, and then and an L2 loss as well. And then for the pre-trained encoders, we tried different diffusion models from the Taming Transformers library. And then we also tried the discrete VAE that was from DALI 1, and then just the raw image. And then for the eval metrics, we used the mean square error and then the 1 minus the SSIM. So, but I'm just showing the SSIM, the rest of it is in the paper. So for the beta ablation, that's the hyperparameter. What we saw was that as you increase the beta, you see that the image-based ones on the top really don't reduce in terms of the error, like their errors don't reduce. But then the well-trained encoder-decoders for different similarity metrics, some of them start pretty high, but as the beta increases, they seem to be pretty robust. The other experiment we saw was like, how much can we scale this up? And so we found that beta as 150 was a reasonable choice. And all of these experiments was done on MS COCO images. And then we saw that as we increased the scale from 6,000 all the way up to 15,000 images, we saw that they all do a very good job at, so I'm showing the 1 minus the SSIM and the mean square error, so lower is better. And then, so for the different diffusion-based ones and the discrete VAEs, we see that they all do a very good job at up to 15,000 images. But the image-based ones, like the raw ones, really never recover, and you get a lot of metastable states. So here is okay, the video works, so that's good. So what we are trying to show here is that if you have the images on the left, which is stored in the memory bank, and then if you give just the raw images in as the query, you see that they don't recover at all. So very soon you see that they enter metastable states. But then if you give this was a discrete VAE in this example, you see that they float around and they have like these recurrent updates, but eventually they do manage to recover all of them. So which was very nice to see. In this case, it's just 100 examples that we're showing, and then you see that they do recover around like the 90th iteration or so. And so that was the first part of like the encoding part of why we, in our exploration as to see how we can improve modern Hopfield networks. The second part is the idea of giving information to get information. So if you notice, the general paradigm here is that if you have to give some sort of a queue to get back the whole image, and in most cases, like in practical cases, if you have a part of the image, you generally have the whole image. That's kind of what it is. So we wanted to explore like cross-modal in terms of like, generally, when you have such images or something, you always have an associative text, which is generally better at, or not better, I would say that you can have access to text more easily. So that was the idea here, wherein that if you ingest both text, which was encoded, and the image, and then you store both of them as a unique association with in the memory bank, and then at query time, you just give the text part and nothing of the image, can you recover the whole image? And the answer is yes. So I gave it away, but that's the whole idea. And so the whole idea was, how do you make these representations? So one thing we explored was that if you have this companion text, so in MS Coco, every image has like 5 captions that's manually annotated. So that was a good example for testing. So one thing we wanted to try was we just hash it simply, and then you take the pixelized token, and then you input it through the same image encoder. And then so if you have this ground truth, and at query time, the blue actually represents just 0 of the image, and then you give only these pixelized tokens, and we see that you run the recurrent updates, and you can recover the whole image. And similarly, the other thing we were interested in trying was that if you use another, say, image text foundational model, so if you use like a clip-based one, only for the image, only for the text, we're not using the image part because we still need to decode and then see how it works. So you have the flexibility as well in that aspect, wherein like we only use the text-based clip representation, and then we use the different discrete VAEs and the well-trained encoder decoders, and then combining them, we see that we can still recover them, so which was very interesting to see. And so like in terms of numbers, so for the clip-based and the scale-out experiments, we see that the different trained encoder decoders can also recover the image accurately, but the image-based ones still didn't do well. And so another question we had was that, do we really care about these unique representations? So in the sense that, what happens if you break that? So when we wanted to try that experiment, so we had this non-unique companion, wherein like we encode like 2 different images with the same kind of pixelized text. And then if you give the blank image, what happens? Turns out that you get a mishmash, or like kind of this, I would say, the metastable representation of like those 2 images. So that was interesting to see. And then in this case as well, you see that although it's a combination, you see some kind of like an odd combination of those 2. And so that kind of tells us that you have to have that unique representation. So that was interesting. So in conclusion, we explored the idea of trying to make content-aware storage and see how practical we can push the Hopfield networks. And so this is a new type of content addressable storage where we call it the Hopfield encoding network. So which is a method of like implicit representation for the storage of the content. And it basically is a flexible chain of an encoder, a Hopfield network, and a decoder. So, and during ingestion, it involves like a pre-processing, a well-trained encoder, and memory to store these representations. And at retrieval time, you can give a portion of the content, which can be from other domains as well. So far, we just explored image and text, but we can do more. And that evokes the retrieval of the encoding, followed by the Hopfield update steps to decode the content and to get the original content without explicitly storing it. And so that's kind of all I had. And then thank you. I'm happy to take questions. So this has been accepted to UniReps this year, and the QR code should give you the paper for more details. I'm happy to take questions.
Questions? Yeah, there's a question in the back.
Thanks for the talk. Great stuff. My question is, can you contextualize how this relates to some of the other content-aware retrieval that exists out there? Is it the main difference that our input here has some missing information and we're trying to retrieve based on that?
Good question. And I want to say that the context, they all are pretty similar, but the main difference is how separable can you make the representations, and the formulations slightly differ. But the main finding here was twofold. One was that if you encode the representations and then you can have a flexible formulation in terms of the different separabilities. Doesn't matter that much. It was pretty robust. And the other idea was that if you can give like the cross-modal part wherein like you can give alternate representations such as text and image, wherein you only give the text portion, as long as it's in the same norm sphere, we found that it does a good job. So that's how I would answer the differences between what has been tried before and like what we are trying now.
There is an absence of search formulation, but this is an energy minimization way of retrieval as against explicit search. There is no explicit search happening. I was just going to say that this is an implicit search type of retrieval rather than explicit search, because you are actually minimizing the energy. The main problem with the basic Hopfield formulation was if the minimization energy landscape is not very well defined, you might end up in these metastable states. And what we have shown over here is by encoding, you are able to resolve the states better. And then the second part, which was if you could, how would you even use the content addressable formulation, was that you give content to get content. But in practical situations, you don't have the content. That's what you're trying to get. So this is the second problem we try to address, is give it some associative content which it's reasonable to have, and then retrieve with that. But the trick is that the two have to be unique, which has some interesting implications for the brain networks as to the cross-modal associations that happen between language and vision, and the uniqueness of these two associations lets you do the recovery.
Let's thank again Kashyap for a great talk.
Thank you.